אוקיי, רואים את המסך?
רואים.
מעולה. אז כן, אז אני רואה רק את חלקכם, אז אם יש שאלות, אז תרגישו חופשי להרים יד וירטואלית, או פשוט אני מניח להתחיל לדבר, ואני אשתדל לשמוע ולענות. אני רואה את רשימת המשתתפים, אז אם אתם עושים raise hand בזום, אני אראה. Okay, so the talk is going to be in English. I'm going to talk about lower bounds for multiplication via network coding. This is joint work with Payman Afshani, Kasper Flexen, and Kasper Green-Larsen from Aarhus University, where I did my postdoctoral fellowship. Okay, so let's start with a simple enough question. So which of these is harder? Is it harder to add these huge numbers or multiply them? So yeah, Kasper actually did the math when we first started presenting this work. So adding the numbers requires a linear number of operations in the number of digits, whereas multiplying them actually takes longer. This is the classic elementary school algorithm, which dates back to Babylonian times. And a very natural question is whether multiplication is in fact harder, or is it just us? Is it the algorithm? So a little bit of history. So as I said, the classic algorithm is originates somewhere in Babylonian times, although it was in base 60, which is very similar to base 10 if you have friends to multiply with. And a conjecture proposed by Kolmogorov in the 1960s, actually in 1960, is that multiplying two n-bit numbers should take n squared. This is the correct time for multiplying. He organized a seminar, and the aim of the seminar was to prove this conjecture. 1 week into the seminar, a young student then, by the name of Karatsuba, constructed an algorithm showing that multiplication is possible in less than n squared time. Yeah, every party needs a party pooper. The seminar was closed due to this result. It didn't achieve its goal, but it achieved something nice, I think. Kolmogorov thought so as well. And it gave rise to progress and research during the 60s and the 70s. This was improved throughout the next few decades. So Toom and Cook presented a better running time, an algorithm with a better running time, and this was improved throughout the years. Most of these algorithms are based on the fast Fourier transform algorithm from 1965. Finally, Harvey and van der Hoeven, so between 2007 and 2019, if you see this log star here, this O notation hides a constant. So between these years, they had several papers improving the constant hidden inside this O notation. And eventually, actually 2 months after we published our lower bound, they published a matching upper bound of n log n, okay, which basically closes the complexity of multiplication, subject to a conjecture, which I will discuss in a minute. And their paper applies also for circuits. So circuit complexity for multiplication is also asymptotically n log n. So a little bit of background. I wasn't sure what the audience background is. So a little bit of background. If you know circuits, then you can doze off for 2 minutes. So Boolean circuits with arbitrary gates. So a Boolean circuit is basically a directed acyclic graphs. In this context, we refer to nodes as gates. So we have input gates, which have in degree 0, and we have output gates, which have out degree 0. All the rest are just gates, and each gate is assigned with a Boolean function. So if the in degree is k, the gate is assigned a Boolean function from 0,1 to the k to 0,1. It can be any function. Okay, so I chose the XOR and the AND just for ease of notation on the slide, but it can be any function. This is what with arbitrary gates means. Okay, so we have this circuit, and I won't go into this formally, but since this is an acyclic graph, then it has a topological ordering. And this is important for evaluating the circuit. So the way we evaluate a circuit on a set of inputs, so we assign values to the input nodes. So here, for example, 0, 1, 1, 1. And we go over the rest of the gates by the topological ordering and evaluate them by the input nodes and the corresponding function. So if this node gets a 1 and a 1, it will be 0, and so on and so forth. Okay, until we evaluate the output nodes. Okay, and this is an evaluation of the circuit. So we have a few important properties of Boolean circuits. The first one is the size. This is the number of nodes or edges. It depends on context and discussion. The depth of a circuit is the longest path between an input node and an output node, an input gate and an output gate. And last, the fan in or fan out is the maximum in or out degree, respectively. Okay, and intuitively, let's discuss first the conjecture intuitively. So the instance for the coding conjecture is a graph with a sequence of pairs, of source sink pairs. Okay, let's assume that they are distinct for this, for the context of this talk. They don't have to be, but it makes notation much easier. Okay, so we have two problems that we can place on this graph. One is a communication problem. Each source needs to transmit an R-bit message to the corresponding target. Okay, an edge E, okay, the graph is capacitated, an edge can pass at most its capacity bits of information, and this is measured by Shannon entropy. Okay, and in this problem, the communication problem, the unique thing about it is that nodes can manipulate messages. Okay, so a node can send a message which is a function of its input. It doesn't just pass it along.
Lior, are you counting rounds of communication, or this is CE per round, or what is it exactly?
No, it's not a round. It's like, you can think about it as a flow of information. I'm not counting rounds.
It's a DAG, no?
It's a what?
It's acyclic.
Yeah.
Okay, so there are no rounds.
It is a DAG. So yeah, but what I'm counting here is the amount of information, of concurrent information that can pass through the graph. It's not rounds of communication. Okay, is that clear?
No, but so you can send C sub E bits of information at a certain time, and then C sub E additional C sub E bits in the next time unit, right? That's the model.
No, so the model is not synchronous model. It's like a concurrent flow. So we pass it like it's very similar. So the next problem I'm going to discuss is multi-commodity flow, and the communication problem is similar to that. So we think about it as a channel that transmits that information. We don't think about it as rounds of communication. We think of it as a constant communication line that transmits this bit or this R bit.
Yeah.
Okay. So it does not revolve around rounds of communication. It's a one-time thing, a one-time pass. That's what I'm counting. And in the multi-commodity flow problem, we need to send R units of flow between sources and targets. And again, this flow has to be sent concurrently by all sources to all targets. Okay, and again, an edge can pass at most its capacity units of flow. Okay, so let me illustrate an example in a second. Just know that this R is not necessarily an integer. Okay, and the conjecture made by Lee and Lee, again, intuitively, we'll formalize it in a second, but that in undirected graphs, the best communication rate is the best flow rate. And let me illustrate it. I think after I give this example, it would be simpler, but I will pause for questions after I give this example. So bear with me just for a few more slides. So we have this graph. This is a directed graph. Okay, so edge capacities will be 1 unless stated otherwise, because I want to remove them just to make slides easier and more easy to understand and read. And we start with a directed graph example, and we have source and sink examples. So these are S1, T1, S2, T2. And we think of the message as if it is coming from an outside source. Okay, and it's chosen from some predefined set. Okay, so S1 gets its message, capital S1, from a set A1. S2 gets its message from capital S2 in A2. Okay, and let's suppose it's just 1 bit for this example. So S1 has to transmit this bit to T1 and S2 to T2. And every node, again, can manipulate its message and decides what message it wants to send to the outgoing edge, to any outgoing edge. Okay, so if the graph is undirected, then the protocol chooses an orientation of the edge. We'll see it in a minute when I give an example on undirected graphs. So this middle node can decide to send the XOR of S1 and S2. Okay, we measure everything by Shannon entropy, so it's still 1 bit of information. And then if we transmit the XOR to the corresponding targets, they can deduce the original message. Okay, note that every path between S1 and between S1 and T1 has to go through this middle edge, this, and every path from S2 to T2 has to go through this edge. So if we wanted to transmit it as is, we needed to transmit 2 bits through this edge. Okay, but since nodes can manipulate messages, we can overcome this difficulty. Okay, and the information rate of the graph is the maximum Shannon entropy over all messages. Okay, so in this example, the flow rate is 1. Now let's look at multi-commodity flow. Okay, so multi-commodity flow, just go over the definitions very quickly. For every edge and every commodity, we have a flow that is assigned to it. Again, in undirected graphs, the flow of each commodity will also choose a direction. So different commodities can move in different directions. Okay, and it doesn't, and they don't cancel each other. It's not like a one commodity flow. Okay, so what flows need to satisfy is first conservation. Okay, what goes in must come out for every node that is not a source or a target. Okay, and they need to satisfy concurrency, which means that the source nodes need to send 1 unit of commodity, and this target nodes need to absorb 1 unit of commodity. Okay, for each commodity, its own pair. Okay, so what can we do here? We cannot do much better than what we expect. Okay, so the blue commodity has to send its 1 unit from S1 to T1 this way, and so does the, I hope it's green, but I'm colorblind, so excuse me if it's not. But okay, so this is the best we can do in this simple graph. Okay, and the flow rate is the maximum R for which we can send concurrently all flows. Okay, so in this case, we can only send 1/2 of a commodity between each pair. Okay, because of the nature of this graph. But note that some edges remain unused. So what happens if we eliminate the direction, if we remove the orientation of the graph? What can we do now? So now we can send half the blue commodity to T2, because now we can move it out of T2. Okay, so we move half the commodity through here, and half the commodity we go around. And we do the same trick with the green commodity. And therefore, we get that we can pass one commodity between each source sink pair. Okay, notice this edge. As I said before, each commodity chooses another direction, but it's like dividing a pipe to two different pipes and flowing liquid in two different directions. The capacity is still one. Okay, so now everything can go smoothly and R equals 1. So this is basically, in a nutshell, this is a proof by example. Of course, the conjecture is not proof. Otherwise it won't be, it's not proved. Otherwise, it won't be a conjecture. But this is, by example, the conjecture. Yes, Uri?
Leon, can you please go back to the previous slide?
Yeah, of course.
So why is there a green arrow between S1 and T2 here?
Because, so we move
okay, yes, yeah,
one
okay.
and we split it.
Yes, I see. Yeah, thanks.
Yeah, no problem. Okay, so basically this is what the communication, the network coding conjecture or the K-pairs conjecture conjectures. Okay, that in undirected graphs, the coding rate or the information rate is equal to the multi-commodity flow rate. Okay, as we have seen in this simple example. Okay, so is the setting clear? So all the definitions, this is basically everything we will need to move forward. Okay, so our result is that assuming conjecture 1, every Boolean circuit with bounded in and out degrees, with bounded fan in and fan out, that computes the product of two n-bit numbers has to have size at least n log n asymptotically again.
Leo, I have a question about the conjecture itself. So
Yeah.
is one of the direction in the conjecture clear?
Yes, so it is clear that if I can pass multi-commodity flow of rate R, I can pass information of rate R because I can just mimic the multi-commodity flow.
But your graph is not the same. You don't have undirected edges, right?
No. What do you mean? The graph, the ground graph is the same. Take this graph, for example. If I can pass this commodity flow, okay, I can always do the same for information.
This is assuming that you still can use edges both ways, right?
Yes, and I can. In an undirected graph, I can.
Okay, thanks.
Yeah. Okay. So, so this is the theorem. Just 3 slides of previous results, a bit of history, and we'll get right to
Just another question, please.
Yes, of course.
So can you go back to the theorem? So do you really need the assumption?
Yeah.
Do you really need the assumption about the out degree?
So yeah, so at least our proof needs it, because what we do is we take the circuit. I don't want to spoil it too much, but we take the circuit and then we remove orientation. And there in the undirected graph, we need the degree to be bounded for our result. Yeah.
No, but can't you always replace the out degree by a tree, and that would only increase the number of edges by a linear factor?
You mean in general circuits, you can just reduce the circuit to a circuit with? Yeah, I think so. Yeah. I need to check it carefully, but I think so.
Okay, thanks.
Okay. Okay, so there were few multiplication bounds over the years, multiplication lower bounds, sorry, over the years. But at least as far as we know, they were for very restricted cases on very restricted models. Nothing very conclusive was known before our result. Regarding the undirected pairs conjecture, the network coding conjecture, so in 2006, Adler et al. Showed that in directed graphs, we showed a gap of 2 for directed graphs. So they showed actually that in directed graphs, we can extend this, this ratio up to a linear factor in the size of the graph. So basically, they used this gadget that we saw and combined it together in a subtle manner to blow up the ratio. Okay, and in 2017, Braverman et al. Showed that for undirected graphs, if we show only a small constant gap, we can increase it to a logarithmic gap in the size of the graph. Okay, so this is regarding the conjecture, but it is not known whether the conjecture is true or not, and nothing has been known regarding this conjecture, the validity of the conjecture. Using the network coding for the data structures and algorithms lower bounds was first initiated by Adler et al., who showed lower bounds for oblivious algorithms computing the transpose of a matrix. Oblivious means that the actions of the algorithms are known before receiving the input. And in 2019, Fahadi et al. Showed lower bounds for external memory sorting using conjecture 1. Okay, and they also, in addition, they showed how to remove the obliviousness requirement from Adler's result, from Adler et al.
So, Leo, what does it mean to compute the transpose of a matrix? You get an n-square matrix as input, and you have to output n-square bits?
Yes, yes.
So,
and
rewire? I mean, I don't understand.
Sorry?
Don't you just rewire? I mean,
so no. So the thing is, it depends on the representation of the matrix. So if you get it in the form of rows, and you need to output it in the form of rows, then it is more difficult. It's not as trivial. So
no.
Yeah,
what is the bit of is word of length n or something like that? That's the point, or?
Yes, so you get a vector as the input, and not point by point. If you get it entry by entry, then it's easy. Then it's just rewiring, as you say, and it's a constant rewiring. It doesn't depend on the input. Okay. Okay, so the shift problem is basically a specific case of multiplication. Okay, so we are given an n-bit string and a number between 0 and n-1, and we need to shift that string left or right, depending on where you look from. And you can see that this is actually a specific case of multiplication because it's simply multiplying by 2 to the n. Okay, that's shifting. So what we show is in fact a bit stronger than a lower bound for multiplication. We show that any circuit computing the shift function has to have size, again with bounded degrees, has to have size at least n log n. Okay, and this is this clear that this implies that the main theorem? Okay. So the basic idea
and here the
sorry,
and here and here the n log n is clearly tight, right? Because it's easy to implement that in using a circuit of size n log n.
Yes, and now it is also clear for multiplication because of the Harvey and Van der Hoeven result. But yeah, this was known before. Yes. Okay, so the main idea behind the proof is that if we have a graph with bounded degrees, then it implies that a neighborhood of specific size cannot be too large. Okay, what I mean by that is that if you have an undirected graph with maximal degree c, and you have a vertex and a distance d, then the number of vertices in this neighborhood, within distance d from u, is at most this geometric sum. which sums up to at most 2 times c to the d. And what this implies is that no more than 2 times square root n nodes can lie within distance log c of n from u, half log c of n from u. Okay, this is the main idea, bear this in mind. And now we go back to circuits. So we have a circuit computing the shift function. And it's, again, bounded degree. So we have the input nodes, and we think of L as the shift. These are extra input nodes. We will get rid of them in a second. That's why they are not specified, each one specifically. So consider for a second the induced undirected graph. So this graph has bounded degree 2c at most. Okay, so for every input node, at most 2 square root n of the output nodes are within distance half log n from x1. That means that for most shifts, x1 has to move its message far. And by far, I mean more than half log n. Okay, and by averaging, we get that there exists a shift for which a constant fraction of the inputs have to send their message far. Okay, now if we go back to the directed circuit, we know that there exists this fixed shift. Let's assume it's 0. And we fix it and we hardwire it into the circuit so we can get rid of it. So this is a circuit computing the L0 shift. And now we remove edge orientation and we construct our communication network. So each edge is assigned capacity 1, and we think of the message as a 1-bit message transmitted to x1 to xn, and they have to transmit it to y1 to yn. Again, we assumed that L0 is 0. Okay, this this shift that requires long distance. Okay, so every source sends 1 bit, and it has to send it to its corresponding target, which means that most sources have to travel far. So if we emulate the circuit, and we are allowed to do that because the protocol in an undirected graph chooses a direction, okay, so we get that this G has communication rate at least 1. But now we apply the conjecture, and we think of the network as a multi-commodity flow network. The conjecture implies that G has at least flow rate 1. Okay, so there exists a flow that sends 1 unit of commodity between each source sink pairs. What do we get from that? So if we look at the size of the graph, the number of edges, then it's exactly the sum of the capacities. And since this is a legitimate flow that moves 1 unit of flow between each source sink pairs, then we get this inequality. And since a constant fraction of the pairs need to travel far, that means that this sum has to be at least n log n. Okay, and we conclude that C has to have size at least log n, n log n, sorry. Is this clear? Are we good? Okay, so now we're going to get a bit wilder, okay, for the next 10 minutes or so. And we're gonna take this one step further. So we introduce a family of depth 3 graphs. Okay, so we have n input gates, n output gates, and we have an extra epsilon n gates for some epsilon smaller than 1. Okay, a little less than linear. And the degree, if we remove this middle layer, the degree between input-output layers, we bound it by C. C doesn't have to be a constant. We'll refer to that later. Okay, so this is the special family we're going to address now. And why this family? So the motivation comes from a theorem by Valiant in 1977, which showed that every circuit computing a Boolean function, which has size linear in n, and depth logarithmic in n can be reduced to this type of circuit. This means that lower bounds on this type of circuits will imply, in turn, lower bounds on linear sized logarithmic depth circuits. So this is why these are important. Valiant additionally conjectured that if C is smaller than 3 and epsilon is at most 1/2, then there exists a permutation that this topology cannot compute. This means that if we fix the graph and we can change the gates, but we fix the topology of the graph, but we change the gates no matter what we want, there are permutations that this topology will not be able to compute, no matter what functions we assign to the gates.
So, Lior, I mean,
Yes.
Doesn't Valiant conjecture also says that you need output-input connections of size n to the epsilon or something like that?
So Valiant actually made 4 conjectures. I didn't get into it, but actually Valiant made in this paper in '92, he made 4 conjectures.
Sorry, I mean the theorem, not the conjecture.
Sorry? Yeah, the theorem. So the original theorem showed degree n to the epsilon, and okay, so let's go back to this. So it showed n to the epsilon, but then it showed that the number of extra gates was asymptotically smaller than linear. With a small tweak, this can be adapted to sublinear, but only in constant, smaller than n.
Something like log 1 over epsilon or something like that?
Exactly. Okay, so yeah, this can be this. It's just one extra step from the original theorem, which we took writer's permit to writer's license. Sorry, to change it a bit. Okay. So what we show is that for depth 3 circuits of this kind, computing multiplication, okay, the number of the second layer gates is at most epsilon n. So we have epsilon, which is significantly smaller than 1/2, but still a constant. And the input-output degree is at most c. Then we get that, assuming conjecture 1, c has to be at least log n over log n. So strictly greater than a constant. So if we revisit the conjecture one more time, what we show is the conjecture is true for C, which is super constant, and for the shift permutations specifically, not for every permutations. In this sense, what we prove is stronger than the conjecture. However, our epsilon is smaller than 1/2. So we have a bound over epsilon, which is 1 over 300 or so. Okay, so this sheds light on the conjecture, but still does not prove or refute it. Okay, so the idea is very similar.
Conditional on the original network coding conjecture, right?
Yeah. We'll still rely on this conjecture. Yeah, sure, of course. So we have again the shift function. So we will show again that it's the shift function that attains the lower bound, and we have no assumption over the extra nodes, the epsilon n nodes. So we might as well assume that every node, every input node is connected to them, and every output node is connected to them. I added only the edges between x1 and y1 because the slide is full as it is. Okay? So this is our circuit that computes the shift function. And again, we want to use the same idea. Bounded degrees imply small neighborhoods. But we can't use this idea here, right? Because if we remove the orientation, even if we don't, every target node is at distance 2 from every input node, right? Through these nodes, everybody's connected to them. So we need to somehow remove them. Okay, so in this graph, everything is of distance 2. So we don't get that small neighborhood property that we wanted so much. So let's ignore.
Just a second. Why are you counting if you're not counting in the C out degree or in degree of these input and output nodes, you're not counting the edges to the middle node? To the middle
No, it's just, so the degree bound is only in this graph. If we remove these nodes and we have the induced subgraph, that's where we have the degree bound. So that the bound on the degree is only between input gates and output gates. Okay, Ani?
But I'm not sure what that means. I mean,
What do you mean?
if you remove
What
the
means?
middle?
Again, sorry?
No, so you have a circuit of depth 3, right? And
Yes.
the second layer, there are gates of arbitrary fan-in. What do you assume about the gates?
Arbitrary fan-in and fan-out. Yes, exactly.
Okay, but every input node is connected to at most C of these gates?
No, so, okay, so every input node is connected to at most C output nodes, and every output node is connected to at most C input nodes directly. But they are all connected through these extra layer. So this extra layer has input edges, incoming edges from all input nodes and outgoing edges to all output nodes. This is the kind
So you have direct edges from input nodes to output nodes, and only in that bipartite graph you have the degree restriction.
Exactly.
I see.
Exactly.
Okay.
And this is, and again, the it might look strange the first time you look at it, but this is the kind of graphs that variance reduction leads to. So they are showing lower bounds on these kinds of graph implies lower bounds on linear size logarithmic depth circuits. So that's the motivation for dealing with them. Okay, and yes, to make things clear, the degree is only bounded in the graph induced by the input-output nodes. This is the problem I have with the bounded degree implying small neighborhoods, because here bounded degree does not imply small neighborhoods. We can always go through these nodes to from any input node to any output node. So I want to somehow remove these nodes, these extra nodes. And this is the first part of the proof. So in this graph, if we remove these nodes, then we have this property that bounded degrees imply small neighborhoods, because here the degrees are bounded. So again, if we concentrate for a minute, if we focus on this graph, then we have the same property as before. Within distance at most d, from any input node, we have at most 2 times c to the d output nodes. And again, this is the undirected graph, so we can go out of output nodes as well. Okay, but if we move only, so this is a bipartite graph. So, but if we move like this, and we move at most distance d, we can only reach at most 2 times c to the d nodes. But that means that at most 2 square root n destinations are within distance half log c from any input node. This is the same conclusion we got to before. Okay, and again, it's important. This is in the induced graph by the input-output nodes. And again, by averaging, there is a shift for which a constant fraction of the input nodes have to communicate their message to a far output node. So we first hardwire this L0 into the circuit. We got rid of this. Now we lay our eyes on these extra nodes, on the second layer, and we want to remove those. So note that these nodes have at most 2 to the epsilon n possible outcomes. Okay? Epsilon n nodes, each one has a bit, at most 2 to the epsilon n possible outcomes. So among all possible inputs, there has to be a set. So there has to be an outcome which is attained for a large set of inputs. This is averaging. Okay, so there exists an assignment to these f1 to f epsilon n, which is attained for at least this much inputs, this many inputs. So we say, okay, we settle with those, we hardwire these into the circuit, and we remove these nodes. So what did we get now? We got a circuit, okay, and let's, just this notation is important, it will follow us. So we denote the set for which this is the result attained for this bit by calligraphic f. So if we remove them, if we hardwire this f1 hat to f epsilon n hat into the circuit, that means that whenever we get an input that is in calligraphic f, the circuit works fine. Okay, because so let's take a look. So if we remove the edge orientations, we add source, now we have this communication network. Okay, and again, we send a message. Let's assume first that the message is from f, from calligraphic f. That means that what the sources will get will be in f, and that means that the circuit transmits them just fine. Okay, so we are all good if the original message is in f. What happens if it's not in f? So the problem is clear. What we have and what we don't have, is that clear? That's a good point for methodic break for questions. Okay, so our problem is with strings or with inputs that are not in f. So what do we do then? So we add this node u, which we think of as an advisor, a supervisor, what you will. Okay, and we connect it to all input nodes. Okay, and this supervisor will make sure that whatever goes into the circuit will be in f. So we add edges S1U, S2U to S1U to SNU that will basically send the original message to U. So they have capacity 1 each. U receives the message, decides whether it's in F or not, and if not, finds a humming closest string, the one that needs the least flipping, that is in F. And then it sends it into the circuit. Okay? And the key intuition, sorry, I skipped it. The key intuition is that since F is very large, we don't have to correct. On average, we don't have to correct many bits. Okay, so since F is large, even if I have a string outside of F, an input string outside of F, I can find a point in F which is quite close to the string on average. That's the intuition. Okay, so we add edges going out from U into the circuit, and we set its capacity, their capacities to C1, Cn respectively, where Cj is the entropy of the indicator for the jth digit. The jth bit is has to be flipped. And as we said, it doesn't. The intuition is that it doesn't happen very often. So these capacities can be small. So we flip the necessary bits. The circuit gets a string from F and transmits it. So what do we need now? The output nodes have to know whether what they got was the true bit or the one that was flipped. So we need to connect U also to the output bits. Okay, so we add red edges of capacity C1 to Cn also to the output bits. So now we flip the necessary bits before going into the circuit. So whatever goes into the circuit is in F, and then we move it because the circuit knows how to transmit messages from F, and then we flip it back.
So, Leo, do you need just one edge from U to each Yi, or do you need C edges?
No, one from each, because yi just gets 1 bit, and it needs to know whether it should be flipped or not. Okay? So it's just one edge of capacity, the maximum entropy of that, the entropy.
The input, you correct the output.
Yeah, exactly. If I flipped it before, I have to flip it when I get it. And this graph has communication rate at least 1, because I've just shown how to transmit this 1 bit from each node. Okay, so by the conjecture, we replace the message with commodities, and by the conjecture, we know that this graph has flow rate at least 1. That means that there exists a flow that it achieves at least 1. Okay, 5 more minutes and we're done. So the main concern here is that much of the flow goes through these edges and not inside the graph where I wanted to move. But what we show is that...
Can I ask you about the connection between you and the output nodes? So it has to be specific to L0, right? It cannot be generic.
Yeah, we fixed L0 before. Yeah. Yes, exactly. So how much flow can go through you? That's my main concern. So if we sum up the capacities of these edges, so we have n because we needed to transmit the original message to you, plus 2 times the sum of these capacities of the red edges. Okay, and that's the sum we get. Now we use a theorem by Fahadi et al. That says exactly what the intuition predicted, but formally, of course. Okay, for every large enough set F, the expected distance of a random point is small. Okay, and this is the expected sum of entropies. So a little more calculation and a bit shoving gets us that the sum of these entropies is no more than the entropy of epsilon over 2 square root of epsilon over 2 times n, which is if epsilon is small enough, this is quite small. Okay, this is smaller than, I don't know, 0.05 or something. Okay, so that means that the entire flow that can go through you is at most 1.1 n. Okay, remember the concurrency, what goes through you has to come out. That means that the amount of flow actually using you can be at most 0.55 n. Okay, but that means that most of the flow has to go through the original graph. And again, I will not burden you with the small technicalities, but by averaging, that means that there is a constant fraction of pairs that have to send a constant fraction of its commodity through a long path. And again, we get the same thing. We get that this is the degree bound. So the number of edges in our graph is at most Cn. Every edge was of capacity 1, and therefore the sum of capacities is exactly the number of edges. We get flow that flows 1 unit of commodity. So we get this inequality. And since a constant fraction of pairs have to travel long to pass the commodity, we get that the sum of these flows has to be at least n times log C of n. Okay, so we got that C times n is at most n times log C of n. This implies that C is at least omega of n log n. Okay, so 2 points regarding, 2 or 3 points regarding future work. So the undirected pairs conjecture is still unresolved. Variance conjecture, we made some progress, but we haven't proved or refuted any of them. Specifically, what can we say about the epsilon to C trade-off? Okay, and one last question is, are there any other interesting functions that have Boolean circuits complexity at least n log n, assuming conjecture 1? Can we use it further? Okay, so thank you for listening. If you have any questions, I'm here.
So, yeah, so Leo, I have a question. So there are lower bounds for that 2 or that 3 circuits which are unconditional. Now, I don't remember whether it's like log star or log log or log. And functions that are related to multiplication, like matrix multiplication. And,
Yeah.
So what are those lower bounds? I just don't remember the exact.
I don't remember by heart. I can check, but I don't remember.
No, I'm on one of those papers and I just don't remember. But that may be a different way of obtaining the same, right? Because multiplication is like multiplying with a n-cell matrix or n-cell matrix.
So yeah, I don't. It's actually so. Yeah, a disclaimer. This is not my main field of research. This is just a problem which I had a lot of fun working on. So I don't do complexity usually.
No, so I think there are n log n lower bound for different functions. So maybe.
Okay. Yeah, maybe. I'm not really sure. So my main line of research was algorithms during my PhD, graph algorithms during my PhD, and then machine learning during my postdoc. But this was like a sidetrack, but I really liked it because this is a result I could explain to my kids. I mean, multiplication is intrinsically harder than addition. This is
How old are your kids, Leo?
What?
How old are your kids, if they can understand it?
Yeah, my oldest is 16. So yeah, but even the young one who is in elementary school saying that multiplication is harder. Yeah, but her answer was, of course it is. Look, so yeah, so she didn't get the full grasp of the theoretical result, I guess. But still, it was cool. I could tell people what I did, and yeah, it actually appeared in. I think in some popular blog posts, which are less formal and more to a wider audience. So yeah, this is the result that got me a bit of fame. So and it's a cute result, but it's not my main line of research.
Okay, any other questions?
Yeah, I want to ask about putting the edge capacities, the entropy on the edge capacities. So how does it even make sense to have this tiny capacity over the edges? Either you send flow or you don't send flow. What does it mean if you're on average sending a bit of flow of having these small capacities?
Okay, so yeah, you got me. You caught me. I tried to sneak that one past you. But so the thing is, so if we go back, let's go back to that for a second. Okay, so yeah, so strictly speaking, you're correct. It doesn't make sense. It feels weird because I'm always sending a bit, right? So setting the capacity to be the entropy doesn't feel right because I am sending a bit. I'm always sending one bit. So the thing is, so I have two answers. One is evading and one is less evading. So the evading answer will say that this is the definition of the communication problem. And I'm covered. This is I'm completely covered by the definition. But when we wrote the paper, we actually didn't feel it was right either. So we felt that this was wrong. So in the paper, what we did was we didn't connect input nodes to U separately. So it's not every node for itself. We collected them into sets, into blocks of 20 nodes. Okay, and 20 is arbitrary, but a constant number of nodes. And there we managed to show that not only the entropy is small, not only we can bound the entropy, we can devise a coding mechanism which always sends, which the expected string, it says, the expected length of the message is small. So not only the entropy is small, but the encoding is small. Okay, in the case I presented it for simplicity, and Actually, most of the times I got away with it. But yeah, but this was just for simplicity. So actually, in the paper we prove that that we can use an encoding which is short and not just the entropy that is small. Okay. Yeah. Yes, Ivan.
Can you say something about what algorithm people actually use to multiply large numbers? Is this the n log n log log n, or?
Use, you mean where? You mean in industry?
I guess in cryptographic software. I mean, I don't know where else large n's arise.
Oh, wow. Now you take me really out of my comfort zone. I have no idea. I must say I have no idea what is the, I guess the simplest one to implement, knowing the industry as I know, I guess the simplest one to implement. That's what they use, but I really have no idea.
Yeah.
I think they use Karatsuba. Karatsuba is actually used.
Karatsuba also in
Yeah.
software or only in hardware?
In software.
No,
Okay.
I think that even one level of FFT is used. So if you just do FFT once, not recursively, you get n log log n squared. And that's actually implementable. I think this is what most packages use.
Okay, thanks a lot.
Yeah, so I'm doing things outside of algorithms, but outside of theory, less much.
Okay.
Okay. Thank you very much, Lior. תודה רבה.